Okay. Today we are going to start the topic differential and total differential. Differential and total differential. For a function of one variable, we say, for example, y is a function of x. For a function of one variable, we already know that dy is equal to f hierarchy y prime of x times dx. And where y prime is equal to dy by dx. So this differential of y is nothing but y prime times dx never. This is the differential of a function of one variable. Now suppose we have a function of two variables. This f is a function of two variables. Let us call them x and y. Although we can extend this idea of differential to this function f, and we call df. Df is called the total differential. So this is equal to del f by del x times dx plus del f by del y times dy. Del f by del x, this is calculated at constant y, and del f by del y, this is calculated at constant variable x. This is called the total differential of the function f. Total differential of the function f. Aduna, one dimension differential idea, we can extend that idea to a function of many variables. So df is called the total differential. Total differential of f. F correct. Although target function of two variables. Function of two variables f is a function of two variables. We can write this as f of x. F of x is partial derivative of x with respect to partial derivative of f with respect to x times dx plus partial derivative of f with respect to y times dy. So an EBI got for a function of many variables, for example, x, which is a function of two variables, x and y, partial derivatives exist so a function is differentiable or even though the partial derivatives exist, a function is differentiable or see, let me show it here. Share the screen. The total differential I could discuss the video df equal to fx dx plus fy dy. This df is called the total differential of f. Next seeing all the existence of fx and fy is not sufficient to guarantee that fxy is differentiable. That is, fx and fy must also be continuous. For a function of many variables, the existence of partial derivatives is not sufficient to guarantee that the function is differentiable. Function is differentiable or partial derivatives exist. In addition to that, another condition is that the function, the partial derivatives fx and fy, they must also be continuous. function is different. Function of many variables is differentiable. Or you have the partial derivatives must exist, and in addition to that, the partial derivatives must also be continuous. For the rest of this section, we shall use the pressure of a gas instead of f of xy to illustrate differential. Differential study the physical example pressure of a gas. So generally, the pressure of a gas depends upon the temperature expressed in Kelvin and the molar volume. That is the volume of 1 mole of the gas. So we can write pressure as a function of two variables, volume and temperature. We already know that at sufficiently low pressure and high temperature, gases obey the ideal gas equation of state, PV equal to RT. So the PV equal to nRT, the N equal to 1 for 1 mole. For 1 mole of the gas, PV equal to RT, where R is a constant whose value is 0.0821 liter atmosphere per Kelvin per mole. At higher pressures, where deviations from ideal behavior occur, the van der Waals equation is often used. P equal to RT by V minus B minus A by V square, where A and B are constants. We shall use these two equations as examples of functions of two independent variables. Equation where function of two independent variables studied over the here P is a function of two independent variables. The independent variables are volume and temperature. And pressure is a function which depends upon volume and temperature. So the S equations 7 and 8 imply the pressure of a gas depends upon its temperature and volume. The total differential of the pressure for a fixed amount of gas is given by dP. Since pressure is a function of temperature and pressure. So we say that, let me come back here. Let me stop sharing and come back here. So is the pressure is a function of temperature and volume. Pressure is a function of temperature and volume. The total differential of pressure, dP, should be written as partial derivative of P with respect to temperature at constant volume times dt plus partial derivative of P with respect to volume at constant temperature times dV. When we consider pressure as a function of two variables, temperature and volume, we can express the total differential of the pressure as this expression. So let me come back to we have subscripted the partial derivatives in equation 9 to emphasize which variable is varied and which is held constant. Physically, equation 9 says that it is an excellent approximation to calculate the total change in the pressure of a gas due to a change in both temperature and volume in two steps. Number one, that due to the temperature change, keeping the molar volume fixed at its initial value. This is how pressure changes with temperature, keeping the volume fixed. And then that due to the change in molar volume, keeping the temperature fixed. This is the second term. This is how pressure changes with respect to volume at constant temperature. Let us consider this example. Evaluate the total differential of pressure for an ideal gas. Okay, let us discuss this example. So let me stop sharing. So evaluate. So what is the question? The question is evaluate the total differential of the pressure for an ideal gas. So we know that the differential of the total differential of the pressure is given by this expression. And for an ideal gas, what is the expression for P? PV equal to, for 1 mole of the gas, PV equal to RT. N to 1 already for 1 mole of the gas, PV equal to RT. This implies P equal to R times T divided by V. Therefore, so from this expression, let us calculate del P by del T at constant volume and del V by del P by del V at constant T. So let us first calculate del P by del T at constant volume. This is, you differentiate this with respect to the temperature T, keeping the volume fixed. So this is nothing but R by V. And very simple. And let us calculate del P by del V at constant temperature. Del P by del V at constant temperature. P is given by this expression. We keep the temperature fixed and differentiate with respect to volume. What do we get? We get minus RT by V square. Minus RT by V square. So we get del P by del T at constant volume, del P by del V at constant temperature. So the total differential of the pressure is given by this expression. We substitute this values here. So R by V is minus RT by V square is and we get the total differential of the pressure for an ideal gas. So let us substitute these values. This is, so let us write it first, del P by del T at constant volume times dt plus del P by del V at constant temperature times dV. And what is this equal to? This is equal to del P by del T is equal to R by V. So this is R by V dt plus del P by del V at constant temperature. Del P by del V at constant temperature is minus RT by V square. So this is minus RT by V square dV. So this is the expression for the total differential of the pressure for an ideal gas. Now let us come back to our screen. Okay, this expression. This is the expression which we have just obtained. We can use this equation 10 to estimate the change in pressure when both the temperature and volume of an ideal gas are changed slightly. We can write equation 10 for finite delta T and delta V in this form. Sigi equation we can estimate the change in pressure when both the temperature and volume. For example, let us use this equation to estimate the change in pressure of 1 mole of an ideal gas if the temperature is changed from 273.15 Kelvin to let me change here. Wait here. So let us use this equation to estimate the change in pressure for 1 mole of an ideal gas if the temperature is changed to 73.15 Kelvin to 274. So the temperature is a slight small change. The volume is small change. What is the change in pressure? We can calculate by using this equation. This is the equation which we have. This is the equation which we have just obtained, and this is an approximation of that equation. So approximation, we can calculate the change in pressure when temperature changes by this amount and volume changes by this amount. We can substitute the values of R, V, RT, and V square, and delta T. Delta T is 274 Kelvin minus 273.15 Kelvin. That will give you delta T, which is 0.85 Kelvin. And what is delta V? Delta V is a change in volume, which is 10 liters minus 9.90 liters, which is minus 0.10 liter per mole, because per mole means this is the volume of a 1 mole of an ideal gas. So you substitute the values of R, V, RT, V square, delta T, delta V, and ultimately you will get the value 0.0294 atmosphere. So this is 0.0294 times the atmospheric pressure. So the change in pressure is 0.0294 atmospheric pressure. This is the approximate value which we have calculated using the total differential. For comparison, in this particularly simple case, we can calculate the exact change in P from delta P expression to the exact change for P. This is a P equal to for an ideal gas, PV equal to RT, therefore P equal to RT by V. This is the final value of temperature times T2 V2. So this is the final value of temperature and final value of volume. So this will give you the final value of pressure. This will give you the initial value of pressure. And we can calculate the actual change in pressure, and that turns out to be around 0.0297 atmospheric pressure. And approximate calculations, exact calculations, they are very close to each other. So we can see that equation 11 gives us a good estimate of delta P. What is equation 11? Equation 11 is this, which is an approximation of the total differential of P. Now, what have we calculated just now? We have calculated the total differential of pressure for an ideal gas. Now let us consider a real gas, which is described by the van der Waals equation. Van der Waals equation or Targati. So first, let us consider the van der Waals equation. This is the van der Waals equation. So let us write it down. Van der Waals equation. The van der Waals equation is P equal to RT by V minus B minus A by V square. This is the expression for pressure for a van der Waals gas. This is also called the equation of state. Where here A and B are constants, there are characteristics of the particular gas. Then dP, the total differential of pressure, is given by this is nothing but this is P, which is a function of temperature and volume. So the total differential of the pressure is dP, and it is equal to del P by del T at constant volume times dt plus del P by del V at constant temperature by the change in volume. Now for a given van der Waals gas, let us calculate del P by del T at constant volume. This is equal to, so let us differentiate this with respect to the temperature T, keeping the volume constant. Here A is a constant, V is a constant, so this term is a constant. So when we differentiate this partially with respect to T, the contribution of this term will be 0. And when we differentiate this partially with respect to T, we will get R by V minus V. Okay. Next, let us calculate del P by del V, this term at constant T. This is equal to, now let us differentiate this expression with respect to V. So this first term, minus RT by V minus B whole square. Then plus twice A by V cube. See, if you differentiate this with respect to V, you'll get this term. Minus RT by V minus B whole square plus twice A by V cube. So now let us substitute this. Now let us substitute this. Sigi values is stops along. Sigi values in a stops along. And what do you get? You get the total differential for pressure is given by R by V minus B dt plus inside bracket twice, let us write this first, twice A by V cube minus RT by V minus B whole square. Let me use the square bracket here times dV. So I have substituted this value here and this value here, and I have obtained this expression. This is the total differential of pressure, which is given by the van der Waals equation. Next up, let us look at another example. A quick case. Suppose we are given some arbitrary expression. For example, suppose we are given this expression, RT by V minus B dt plus RT by V minus B whole square minus A by dV square dV. Suppose we are given this expression. You compare this and this, these two are different. And say expression question determine the equation of state that leads to this equation. Find the value of the function P which leads to this expression as the total differential of that P. P expression such that this expression is the total differential of P. In fact, can we even find a function P whose total differential is given by this expression? I repeat the question. Can we find a function P whose total differential is given by this expression? Does there exist a function P which total differential is given by this expression? Suppose that there exists such a function. Let us call that function P dV. Function to exist then its total differential should be equal to dP equal to del P by del T at constant volume dt plus del P by del V at constant temperature as dV. Now, if such a function exists, then its total differential should be given by this expression. Now, now you compare this and this, compare this and this. You compare this and this, this and this. This will be del P by del T. This will be del P by del V. So in thermodynamics, the mixed second partial derivatives are equivalent. in thermodynamics, oh, mixed partial derivatives have the del 2p by del v del t. First, you differentiate p with respect to t. First, you differentiate p with respect to t at constant volume. This will be a function of t and v again. So now you differentiate this with respect to volume. Volume the differentiate our keeping the temperature fixed. In thermodynamics, most of the time this is continuous. In thermodynamics, most of the time this is continuous. Mixed second partial derivative mixed second partial derivative to del 2p by del t del v. What will be this? This will be first del p by del v. Del p by del v at constant temperature. Del by del t at constant volume. If these two are continuous, if these two are continuous, in thermodynamics, these two are most of the time continuous and these two are equal. See, anisi manayaba. Oh, adu targadi. Aina hojiki mamang the hot cuba. Hojiki mamang the hot cuba for yang as a hojiki mamang the hot cuba. This. I could see expressions of Piramaga. I could hang in ever. Can we find a p? Can we find a function p whose total differential is given by this expression? If such a function exists, assume you compare this and this. So this means del p by del t at constant volume is RT by V minus B. Del P by del V at constant temperature is equal to RT by V minus B whole square minus A by TV square. Sigi P exists over target. I condition satisfied it should satisfy this condition. The second order partial derivatives, mixed partial derivatives say IC orders interchange to Uganda, value anise manana pangadabane. For this given example, let us check whether this is true or not. So first del P by del V, del P by del T, so let record del P by del T. So let now differentiate with respect to V. So let us differentiate this with respect to V. So del by del by del V del by del T at constant volume, constant temperature. This is equal to del by del V. What is del P by del T? It is this. RT by V minus V at constant volume. This is calculated at constant, this is calculated at constant temperature. So you take temperature as constant, you differentiate this with respect to volume. What do you get? This is minus RT by V minus B whole square. So we have obtained this expression. Now let us calculate this expression. What is it? Del P by del V at constant temperature. This is the P. So let us calculate del by del T. See what's happening. Del by del T, del P by del V at constant temperature, constant volume. This is equal to del by del T. What is del P by del V? Del P by del V is given by this expression. RT by V minus V whole square minus A by TV square. This calculated at constant volume. So at constant volume, this turns out to be, when we differentiate this with respect to temperature, we get R by V minus V whole square. When we differentiate this with respect to temperature, I get minus T square. So minus T to the power minus 2. This will be minus plus A by T square V square. So for this given expression, we have calculated the mixed second derivatives. When we compare these two, we find that these two are not equal. We see that the cross derivatives are not equal. So the given expression is not the differential of any function P. Sigi anisi manarga, differential of some function P. This given expression cannot be written as the differential of any function P. Sigumba differential inexact differential, inexact, INEXACT, inexact differential coefficient. Inexact differential. This expression cannot be written as the total differential of any function. Expression it cannot be written as a total differential of any function. Such expressions are called inexact differentials.